Good morning, everyone, and welcome to today's DIH talk. My name is Santiago Uribe Diaz. I am a digital transformation advisor at Lux Innovation. For those of you who are new to these sessions, there is a discussion window where you can interact throughout the session and post messages. And we also have a questions button where you can enter all the questions that you like. And at the end of the session, we will have a Q&A with the speakers where they will gladly answer to all your questions. Today's topic is the different types of 3D printing. This is an interesting topic because it's a trending technology in the industry and it allows to construct pieces that were not possible before with conventional machining methods. And it has a wide range of application. It can be applied to the health tech industry, to the aeronautics, defense, automobile, a very wide scope. So let me talk to you a little bit about the DIH and our services. The DIH is the Digital Innovation Hub in Luxembourg. We are an organization 100% financed by the EU and Luxembourg, so our services have no invoices or administrative procedures. And the goal of the DIH is to digitalize the companies in Luxembourg, and we do it in many different ways. We have the assessments. These are questionnaires that you can fill in our website or with our help in your facilities. And the idea of this questionnaire is to tell you in which direction you should focus your next digital projects, depending on your answers. Maybe you find out that your company needs in priority to focus on cybersecurity or on an ERP system or sustainability and so on. It's a very good guide for you to start your digital journey. Then on cybersecurity, we work together with the Luxembourg House of Cybersecurity. They also have an assessment completely focused on cybersecurity. So if you answer these questions, you will find out how good or how bad are the cybersecurity policies of your company. And once you answer the questionnaire, you also have access to a workshop with them. And a person from the LHC can come to your facilities, take a look at the report from this assessment, and give you concrete solutions and concrete advices on how to make a better cybersecurity in your company. Then for the skills and trainings, we work with the University of Luxembourg. So they can help you identify what are the training wishes of the people of your company, of your staff, and also what are your needs as a company, in which topics would you like your employees to be trained. And they do a match with this information and they can supply you a training roadmap for the trainings of the next year on your company. Then on technology tests, we work with the LIST, the Luxembourg Institute of Science and Technology. Throughout the year, they do workshops in which they teach about trending topics in the industry and technology. And these workshops are very interactive because if you assist, you have a laptop provided by the LIST, and everything the instructor is showing, you can test yourself. He will guide you through and teach you how to use these solutions. And they also have the Test Before Invest program. So this is also very interesting. We know that all the digital projects represent considerable investments. So if you have something in mind, if you want to invest on an ERP system, on a robot, or anything that has to do with digitalization, you can reach out to the LIST and they can help you test this technology before you actually invest on it. And they can use the data of your company and guide you through this analysis. And then after the workshop, you have let's say a better position to decide if you will invest or not in this solution. And finally, we also help with awareness on funding. We have similar webinars like the one we're having today, but completely oriented on telling you which are the funding opportunities presented by the Luxembourg government and the EU. And now, before introducing you to our speakers, I want to ask your help. We're trying to identify which is the preferred language for these sessions on the future. So if you want to vote, it would help us a lot, and it's very easy. You just need to scan the QR code that you're seeing in the screen. And to answer, what is your preferred language, English, French, or German? So I leave this for a few seconds before introducing you to our speakers. Thank you very much. So now, please help me welcoming the speakers of today. We have Maxime Delmet, who is CEO and founder of AM4AM. And we also have Jean-François Sun, who is Deputy Director at Semaform. Welcome.
Thank you very much. Welcome, everyone.
My pleasure. The floor is all yours. I put your presentation.
Thank you.
Welcome.
All right. Thank you very much, Santiago, for the introduction. And thank you to Lux Innovation and the DIH for hosting this webinar. It's a pleasure to attend and to present you about the different type of 3D printing. What we'll do first is introduce our respective company from myself and Jean-François. And so if I may say a few words about mine. So we are AM4AM, company incorporated in 2019. So nearly 7 years of existence. We are located in Foots, Technoport. Our main activity is the production of metal powder for additive manufacturing. So we are a company specialized really on the metal parts, giving our customers the best materials possible. We are still a small team, but growing 8%. Here at Technopole, we have 600 square meter with 35 machines for powder production, 2 printers evaluating the properties of the final parts, everything in-house to be able to have the highest capacity of development possible. And also we still have a good machine for the production of our final product with a capacity of 36 tons per year, which already represents a good amount compared to the global market. And our customers are more present in the defense space or motorsports sectors. So this is for my company and AM4AM. If you want to know more, you can go on our website. And I'm giving the floor to Jean-François from Semaform to present his company.
Good morning, everyone. My name is Jean-François Zun. So who is Semaform? Semaform try to accelerate your time to market with cost-effective production. We are a workshop. We are a family business company based in Luxembourg. And we are also located in the US and in Czechia. And we specialize in precision sheet metal fabrication, machining, and metal and plastic additive manufacturing. Semaform's industrial activities date back to 1916, and with over 100 production machines and advanced 3D printing technologies, including SLM, SLA, and FDM, we support customers from design and prototyping to serial production, even in 3D printing. And we serve demanding industries such as automotive, hydrogen, defense, electronics, metallurgy, delivering high quality and innovative manufacturing solutions.
So good. Now that the presentation are done, let's move to the global content. So we'll start first by an introduction about the different type of 3D printing and what they enable. Then we have a first comparison between machining and traditional manufacturing versus 3D printing. 3D printing is good, but there is also limitation, and we will talk about it and how the industry is addressing this challenge. AM4M and Semaform will present some of our use case, and then we have a conclusion, and we'll be open for a Q&A. So let's start directly with the introduction. So 3D printing is a new way to produce parts layer by layer. It's called additive manufacturing because we are adding one layer on top of another layer. That's the basic principle. And basically, this technology now allows you to print really different materials. So from plastic, that everyone knows, plastic or polymer, which is the most widespread technology, it has become really a standard. You have also metals, and we'll talk a little bit about metals today. It's more expensive, but definitely higher performance. And you have less common material that could be printed. For example, ceramic. It is more and more used for certain application where heat and wear resistance are needed. Glass with transparency and need some precisions. You have concrete. I think most of you have seen on the social media these buildings that are built right now with Crete 3D printers. It is really helping for large-scale construction with different size and increase the speed. And also, and it is not anymore science fiction. We can print organs for regenerative medicine. A lot of studies are done at that level, and some companies are already working on the commercialization. So you have to know that with these different materials, the two first, so plastic, polymer, and metal, clearly represent 95% of what is printing currently on the planet. And so we will focus on these two because they are the most widespread. And I'm giving the floor to Jean-François to talk about the plastic and polymers.
Thank you, Maxime. So about the printing in polymer, you have an overview of three main processes used mainly in the industries. So most of you probably know better or more than the other, the FDM. So it's the most economical solution for prototyping and tooling. It's called fuse deposition molding. So FDM works by extruding a thermoplastic filament through a heated nozzle. So the material is deposited layer by layer until the final part is built. You can choose, and there is more and more material on this sector and process. You can print with PLA, PETG, ABS, ASA, nylon, carbon fiber, reinforced polymers. And this process is really not expensive. You can find some machine on Alibaba or in Chinese website for some dollars or euro, and it's very easy to supply. So we add some OEM manufacturer of such machine for you guys to see and maybe to have a look on the website. Stratasys, Ultimaker, Bamboo Lab, Marketport. So it's a lot of, and so the main field of application is really the prototype, the maintenance, and all the simple use in a workshop. So I think most of you knows this. And the other one is more the SLA, stereolithography. So SLA used a UV laser to selectively cure a liquid photopolymer resin layer by layer. So this process allowed to use engineering resins, including standards, tough, flexible like TPU, transparent, or high temperature grades. So this process is more focused on visual prototypes, dental master patterns for casting. Maybe I had some other like manufacturing electronics, of course. And SLA provides, from my side, the highest precision and surface quality. So more focus on complex geometry that requiring fine details. This is all we can describe the SLA. But the other thing is keep in mind that there is chemical products and liquids to manage. So for smelling, for the environmental, for the safety, be careful because sometimes it's tricky and you have to follow the rules and the law from the countries, of course. And I continue with the selective laser sintering, SLS. For me, SLS is the high level of 3D printing polymers. Why? Because with SLS, you don't need to use support structures. But SLS, called selective laser sintering, use a laser to selectively fuse polymer powder particles. So as I said, this process is eliminating the need for support structures. So it's very, very interesting. But the cost and the investment is quite high. SLS offers, I would say, the best balance between design freedom and mechanical performance for industrial production. And we can speak about for the material, we have PA12, PA11, glass-filled nylon, TPU, PEEK also. So there is a huge also and more material that is coming on the market. But the cost, of course, it's quite high. You can see also OEM for both SLS and SLA. And the SLS is mainly used for the space, medical, automation, and consumer goods. So I hope not forgetting something. So I think you have a global overview of the three main processes in polymer.
So let's move to metal, which is a little bit more my field. Let's first start by presenting you for metal technology that represent the most common technology present in the industry. I want to first introduce each of them by explaining how it works. So the first one and the most spread is laser powder bed fusion. So the idea is you will create like something that we called a bed, which is basically an amount of powder with a flat surface. And you will be using a laser to melt this surface on a different design. And then you will spread one new layer of powder and do another design. And this is how you're making grow your part, by adding layer and making melt only the powder that is needed for the part. Then you have the direct energy deposition. You are then sending powder or filament within the focal point of a laser. When the material is reaching this focal point, it is melted and could be deposited on a surface. This is how you make grow the part, by sending filament or powder in the focal point of a laser and having it melted and deposited. The binder jetting is another technology. It uses a mix of polymer and metals with what is called an ink, and the ink will bond the powder composed of metal and polymer together. Then when you have the final part, it is obviously composed of polymer and metal, and you are desintering with furnace and with chemical actions and removing the polymers and then curing with thermal treatment the final metal part. The last one is called cold spray. The cold spray consists in sending metal powder at supersonic speed in order for them to deform and to stick on a surface. So the idea is using the speed to make it deform and stick to the surface, and you can make your part grow like this. So you have different techniques, and obviously these techniques own several advantages or inconvenience compared to one another, and depending on the application or the parts you want to make, one will be more adapted than the other. For example, for the most widespread, the laser powder bed fusion, the main advantage is you got the highest precision and design of freedom. So you can really have extremely precise details and structures like lattice structure, for example, done with this technology. In the same time, the inconvenience is it is slow, the machine, and running the machine is really expensive. So for making parts that have not a high degree of complexity, it's going to be complicated to use it and to have a viable application with it. The field of application we have for this are typically aerospace, high performance components, racing, motorsports, and all of these. So I've said it, the parts are costly, really costly, but they are performing pretty good. If this technology interested you, these are supplier here, SLM Solution, EOS already show. There are many others. And once again, it is really specific in terms of size, in terms of what you're looking for. And this really requires an expertise to choose the correct machine, and it needs to be guided. For the direct energy deposition, the main advantage is you can do large parts and you can repair parts as well. So the limitation in size that we have in the LPBF, which is the size of the machine, here the DED is controlled by a robotic arm. And basically there is no size limitation except the size of your robotic arm. If you want a 200 meters robotic arm to do a bridge, it is in theory feasible. So there is no size limitation. The main inconvenience of this technology is that the surface finish is really rough, and the quality is really low at that level. It is really done for bigger parts, and the accuracy is also really limited compared to the previous technology. Field of application: large parts, repair, reparation. There are use cases like in Amsterdam, there was a bridge that has been built by this technology in metals. Really impressive. The part cost is a little bit lower than the previous technology, and if you're looking for some OEM, MX3D or Aconity could be good partners and good company to look at. Next technology is the binder jetting. This technology owns a big advantage is that it is really fast. So it has a high productivity, and for some sectors where cost is really important, it is the most favorite technique because you will, as the productivity is high, the price per part is really low. The inconvenience, as I explained in how it works, is you need a debinding sintering process. So you're adding one process, and so it needs a little bit more investment in terms of equipment to have something, and you have to take care about the shrinkage. Obviously, when you remove the polymer, the part is gonna be smaller after curing, and this is something that often has to be taken into account. The field of application, a lot of automotive manufacturers are investing in this technology because basically it has really the potential more than the other to solve their problem of productivity and cost per part. As I said, the cost per part is still more important than for the polymer, but is really the lowest in the metal world. And you have some OEM like HP, the well-known computer company, and X1 as well. Last one, cold spray. So main advantage, you have low thermal distortion because it's so cold, as in its word. It's a cold process, so you don't have any heating involved in this process, and so it could avoid some distortion that you are seeing with thermal stress. Inconvenient, you have less geometric complexity, and obviously as the DED, direct energy deposition, the accuracy compared to the other techniques is lower. It is also limited to material that could properly deform. A material that is too rigid, let's say, won't deform and won't be able to be used by this technology. Field of application, reparation, coatings, and large components. For example, there is a company in the UK. They have put this kind of machine in a big container, and it has been delivered to the army to repair things on the nearest point from the battlefield. So this is a use case that is really interesting with this technology. The part cost is a little bit higher, and if you're looking for some OEM, Titomic or Impact are a good company to look at. So there are other techniques as well. They are less known, that this represent the major techniques in terms of metal and what Jean-François presented in terms of polymer. So this closes the introduction, and we will now talk about the comparison between the well-known conventional manufacturing machining versus 3D printing, and I'm giving the floor to Jean-François.
Yeah, thank you, Maxime. So if we compare both processes, it's quite difficult, maybe impossible to compare, because if you know a little bit football, we are comparing a goalkeeper with a striker, or reverse, a striker with a goalkeeper. So both are really the best, or very good, but they just not playing at the same level or at the same challenge, and they solve different problems. So for instance, if we compare a little bit CNC and 3D printing, if we are speaking about engineering, at school, our teacher asked us to think and to build and to design parts and to know how to produce such parts. But now it's not the case. We can forget what we learned at school, because with 3D printing, we can really focus on designing a part exactly with the functionalities that the part has to reach. That means we have really quite unlimited virtually unlimited possibility of designing thanks to 3D printing. So this is a huge difference. And if you understand that the part that you are creating is really an added value immediately at the design phase, the game is win. So it's very good. So this is the best case. Of course, if we compare the material, the CNC, you have a big, large possibility of material to choose. In 3D printing, it's quite more difficult because you have powder to buy with granulometry, with specification, and sometimes it's more limited to supply and to deliver. If we speak about waste material, of course, the CNC wastes more material than 3D printing, because the 3D printing also can reuse the material that it's used. So on this topic, 3D printing is really the best. If we spoke about an assembly of different parts, or a part to be assembled, if you try to machine such part, you have to machine each part maybe and make another one to assemble it both and together. But with the 3D printing, we can design an assembly and a complex with multiple function to just one single part. So it's more easy, really more easy to produce. Another topic is the internal features. So with the CNC, we are always limited with the tooling we are using, the drill holes. But if you see 3D printing, we can really think about channels, lattice. So I will show you an example just later, so you will understand very easily. We can add really functionalities and solve topics immediately at the first step of the designing of a part. Finally, if we speak about finishing, the finishing in CNC is very good compared to 3D printing. So this is, we will come back maybe later, but 3D printing, it's not very good on this topic. So we will speak a little bit more later. And if we take a cost, and if we want to produce a very, very high complexity part, probably this high complexity is not possible in a machining process. So you will have to switch and to think, to build and to produce this part with 3D printing. But the cost, of course, will be higher, probably. But if you combine all the functionalities and if you see the global cost, maybe the cost will be not so high. So it's really depending on your challenge you have to solve. So here you can have just an example of a part which is produced in 3D printing. So if you see this part, you can see this part with two different thickness. You have a thickness of 0.3 millimeters and a thickness on 0.6 millimeters on one side, on the left side, on the right side of the part. And if you see also, you have a flat surface, you have waves, and you have 3D complex shape. So if you see the numbers of parts that we can print each part differently with a functionality that is different one part to another one. So we can really print 3D complex geometry quite interesting in terms of accuracy. And as you can see, this part is not possible to be machined. So this is a perfect example. So if we move to the other slide, I just give you an example. If you see the Mother Nature, the nature solves so many things. So if you see, nature has already solved the challenge of achieving high strength with minimum weight. if you see bone structures, coral, many biological systems, they are very excellent example of lattice architectures. The subject I talk about earlier. And today, additive manufacturing allows us to reproduce this complex structure and optimize weight, stiffness, energy absorption, and material consumption. As you can see, there is a picture, a topic of different lattice, and we have not enough time to develop all the possibility with the lattice, but maybe most of you knows a little bit about strut-based lattice. You have a planar lattice, TPMS lattice. The TPMS, it's the triply periodic minimal surface, geodit or Schwarz diamond. So there is a lot of possibilities to use lattice with the 3D printing systems. But if one day you have to design such parts and to think about, please keep in mind that you have also to keep in mind to remove maybe the powder, because you will achieve and you will solve a challenge, but maybe the challenge will be to remove the powder and don't let the powder inside the parts. So this is something maybe to think about also on the first step of the designing of the part. And maybe we have also to think about how to clean also the part. Maybe it would be tricky to achieve such challenge too, and also reduce the peak stresses. This is also another subject maybe to follow and to keep in mind. So this is what I would like to conclude with this slide. We can move forward.
And then I will talk about the limitation and the challenge, because 3D printing is I think at the end of its first phase of development, where now we have solutions that are working well. There are still challenges and limitation for its expansion to the global industry, let's say. The first one we want to highlight is the production speed. So for serial production, it's light and large scale, production. 3D printing is still limited because it is built layer by layer, and so it is significantly slower than the conventional processes. And so the challenge is to find viable application for now of 3D printing where the cost where this limited production volume could fit. And there is a lot of research to work on this problem, and how the industry is addressing it is most of the time for metal they are using multi-laser. I think the last 3D printers for laser powder fusion that has gone out in China were with 64 laser, which is enormous to boost the capacity of production. Try with larger volume, also a larger machine to be able to put more parts on a build plate, having higher deposition rates, having post-processing that has to be reduced. And this as a whole is how the industry is working on this production speed problem and limitation, let's say. Then you have a limitation about the materials. Basically, if I'm talking about my field, metal, we consider that 2% of the metal that are used in the conventional industry could be printed currently. So it is really limiting the range of material and the possibility for the industry. And one material could not be directly put in a printers to be tested and to be used. It is a little bit more complex. And so it is one of the main challenges is to supply something that fits with the requirements the industry has. And how we address, and this is the topic of my company, but I will go a little bit deeper in the conclusion, is that many material suppliers as us and machine manufacturers are working on expanding the material portfolio, and the mindset on this topic is not anymore to take a material from the conventional manufacturing and to put it in a printers. It's more to develop something that will be directly tailored for the additive manufacturing process. The next limitation is the variability. So it could be really difficult to ensure consistency between machines, between batch, between production sites, from one machine to another with a batch of material and another. So 3D printing stays a complex process with a lot of parameters that has to be controlled, monitored, assessed, and it's still a very important limitation for the industry is we are doing the same part every time, every day in every factory. And this is the main challenge for the industry and to be able to produce at large scale. And how the industry is addressing it is mainly having process monitoring. So there is more and more in situ monitoring and in situ measurement. There is not yet so much standards in this field, as the field is quite new, and there are a lot of initiatives in trying to have calibration and standards. Here it is written on the slide, machine calibration, but it is going way beyond that. It's not only the machine, it has to be the entire workflow and the entire supply chain that has to be calibrated with standards. And we can also think about different digital tools like digital twins or AI-driven process control or predictive, which are areas that I think all the company working in 3D printing should at least be aware of it, or invest some money to enhance to decrease the variability and enhance their production quality. In terms of quality, I let Jean-François talking about this.
Yeah, thank you, Maxime. Yes, about the topic of quality, probably is the main issue in the 3D printing. We have been in the 3D business industries over 12 years now, and I would say that sadly, maybe the quality is good, but it's not improving so much. So the thing is, we are still facing about surface finishing, the dimensional accuracy, and sometimes porosity, but it's quite under control, and residual stresses. So if you have a very high specification, this is something really to think about, because this is really the topic to improve in the future for the manufacturer. And the challenge we have to move in is to add inspection, of course, and maybe to add also a post-processing systems. So we need sometimes to add a chemical polishing process after the 3D printing. Sometimes we have to mill also the parts to completely find the specification of the customers, but the cost will really significantly will increase a lot. So it's really depending on the specification of the customers. But of course, we have microscope and 3D where we can really follow and take under control all these aspects and see where we have to improve. Of course, we have the parameters that we have to target and to challenge. But as I said, this is for me the main problem. So I would say I hope that in the future the AI, the sensor, the cameras will improve and will be more there for us to help us to improve this topic. So this is, and another point, of course, is the cost. So the cost, it's really depending on what the equipment we are working with, the materials, of course, the labor, and of course the post-processing we just discussed about earlier, because of course the investment are really high and the cost can be more important. The challenge is for the industries, it's really, of course, to have a clear return on investment. I think a lot of manufacturers are trying to make the improvement about the prices, and I think we will reach the cost, the problem of the cost sooner. A lot of big players in automotive are really believing that the 3D printing are a key for the future. So they are thinking the cost is there. And for instance, if you see SpaceX, you have the Raptor 1, 2, 3. If you have a look on the internet, you will see a video where we can follow and see the evolution and the improvement of the 3D printing and the parts that is using with SpaceX. Just to let you know. And yes, about how the industry is addressing it, companies focus on high value applications, part consolidation, of course, design optimization, of course, and increase automation to improve economic competitiveness. So the robotics are coming, as Maxim said, and AI is coming too, so it will help a lot in the near future. So maybe I will continue. Thank you. I can just show you a user case. So a customer asks us to obtain a polymer injection mold insert faster and at a lower cost than conventional CNC machining. So this project is a great example of how additive manufacturing can improve traditional manufacturing processes. And our customers, Serveplast, challenge us. This mold is using for polyethylene production. And they ask us to have a lower cost and to get the mold very, very fast. That's what we did. So we redesigned the insert. We integrated additional functionalities that would have been difficult or impossible to reach with a CNC machine. And the technology allows greater design freedom and faster design iterations. So as a result, the mold insert was delivered in just 2 or 3 days with a production cost, which were reduced by approximately 30%. And the solution was fully validated and implemented in production. So this is a demonstration that additive manufacturing is not only a prototyping tool, it's a real production technology capable of reducing lead time, lowering costs, and improving product performance.
And so I will also present you 2 use cases because we are focused on explaining you the techniques and how it works, what are the limitations, but what is it useful for is also important. So here we have a part for an electric motorbike, 200 horsepower, so already quite a big motorbike. The idea behind this project is that the battery of this electric motorbike were quite heavy, and we wanted to reduce the weight of all the other components to maintain it a good driving on the road. And you have on the far left the machined classical part, and then you have the process that make it lighter, and we achieved to cut the weight by 50% while keeping the same mechanical properties with high temperature with our aluminium material that we have developed here in Luxembourg. The added value of the additive manufacturing here is that the form that is used could not be enriched with traditional manufacturing. And so this optimization and this weight reduction is something that you can only achieve by additive manufacturing. The second use case I want to expose to you is a use case from one of our neighbor, Lunar Outpost. They are manufacturing lunar rover for moon exploration. And in the space sector, every grams count. It is costing a lot of money to send 1 kilo to the lower Earth orbit with SpaceX, but you can imagine if you have to send something to the moon, we are talking about hundreds of thousands of euro or dollars. And the idea is to be able to optimize as much as possible the weight of this rover. And we achieve a weight reduction of this component. This component is the support for the mirror above the condensator. Condensator is the small solar panel which supply the electricity for the rover, and there is a mirror that condensates the solar rays on the solar panels, and we cut the weight by 30% while keeping the same mechanical properties and everything constant, even at low or high temperature, which is something you can meet on the moon surface. So these are 2 use cases that show the potential and actually viable application for 3D printing, where it really makes sense to switch from conventional manufacturing to advanced one. Let's conclude our presentation here. I think it's already close to noon. The key takeaways that we want to highlight for you is that at the current time, there is not a single additive manufacturing technology for all the application. So choosing a technology is really dependent of the material, the geometry, the size, and the cost constraint that you have. One technology is more adapted to one application, and so choosing a 3D printer, if you have special requirement, is requiring a little bit more reflection than only going for the conventional one. The comparison between conventional machining and additive manufacturing is quite tricky, as they are not really solving the same problem as Jean-François highlighted. Additive manufacturing is adding value with complex geometry, lightweight structures, and also on-demand production. It will avoid you to have big halls, big workshops with spare parts, as you can print on demand and locally as well. Additive manufacturing is still facing some challenges with production speed, material constraint, variability, quality, and cost. But also we wanted to show you that in the industry there is also viable application that are already present with 3D printing make more sense than conventionally manufacturers. These are the key takeaways we wanted to highlight for this presentation. And I want to close this presentation in explaining what our respective companies are bringing to this market and to this sector. So my company, AM4AM, our global goal and vision is that we have patented a technology that has the potential to expand the material range and to issue new material with change of paradigm in saying you can't translate material from the conventional to the additive world. It has to be taught for additive. And basically our process has been designed like this, and our material are designed to be directly adapted to the additive manufacturing technology, which will bring more sustainability, cost-effective technology, and also accessible with circular materials.
Yes, from my side, at Semaform, the key is selecting the right technology for the right application, as Maxim said. And our role in Semaform is to bridge the gap between innovation and industrial production. We really try to accelerate your time to market at cost effective. And we combine engineering expertising, metal and plastic additive manufacturing, machining, and sheet metal fabrication to deliver the most efficient solution for our customers. So we're really transforming innovation ideas into industrial reality. And I would say finally, additive manufacturing is not about replacing traditional manufacturing. It's about expanding what engineers can achieve. This is maybe the final topic.
So thank you very much for our attention. And if you want to continue the discussion further, please reach out to us. We'll be happy to discuss more with everyone. And once again, thank you for Lux Innovation and the DIH for hosting this webinar. We were, from my side, but I'm sure Jean-François is saying the same, really happy to give it.
Yes, of course. Thank you.
Thank you so much, Maxime and Jean-François, for this interesting presentation. It was a pleasure having you on today's DIH talk. Before we leave, we have a question from Fabrice. Hello, Fabrice. Well, first of all, our apologies for the technical issues. We will work so that this doesn't happen in future sessions. And to answer, I will read your question to have an answer from our speakers. Fabrice is asking, what is the average number of parts to be produced where 3D metal printings is more interesting in terms of cost compared to subtractive manufacturing in case of metal printing?
If I can say something, if I can answer.
Of course.
I would say it will be, with the 3D printing, it will be linked to the dimensions of the base plate that you are using on the 3D printing processes. If you have a small base plate where the parts are printed, you will have a limited solution access. And if the base plate of the machine that you are choosing is bigger, of course, you will get bigger result. So I don't know if I well answered the question. So 30 by 30 centimeter. Yes. So this is something we can discuss with. Yeah.
If I may, I add something. For me, it's not really straightforward. because as Jean-François said, the average part number will depend on the size of the build, but also the complexity of the part.
Yeah,
I think each part should be reviewed and each part should be analyzed as a unique thing. There is no tailor solution for that. I think it should be an investigation for every part in terms of complexity, in terms of size, and also the capacity of the machine. So it's really hard to give you a concrete answer without having the special requirements and exactly what is the parts and the goal to be produced.
Thank you for this answer, Jean-François and Maxime.
you're welcome.
And again, thank you so much for having participated today. It was really a pleasure. And just to conclude, I leave you this QR code where you can scan, and it will take you to the DIH page, and there you can see all our next webinars and events. Next week there is Nexus, so if you happen to be there, please visit the DIH booth. We would be very happy to talk with you. And thank you, everyone.
Thank you.
Thank you. Bye-bye.
Thank you. Nice day.